You got a couple of those like that, right?
Hey, Tony Anthony is joining us, talking about VFDs tonight. Phil? You're going to teach us about VFDs tonight. Tony, thanks for coming tonight.
Nice to be here. As you said, my name's Tony Anthony. I'm with Yaskawa Drives. I'm the factory sales engineer for Western Pennsylvania, Eastern Ohio, and West Virginia. I do both industrial and commercial. A little background about me. Y'all hear I kind of sound a little different than y'all do because I'm originally from South Carolina. But I've been in Pennsylvania since the end of '91 after I got out of the Navy. And I was in the Navy on operating nuclear power plant on submarines and an electrician. So been doing drives now for 20-something years, and I've been with Yaskawa for 12 and a half years. So tonight we're going to cover basically the basics of a drive. Some of this you're going to find pretty simple, pretty basic, and some of it, we'll get into it. Feel free to ask questions. The more questions you got, any questions you got, that's fine. Let's make this a dialogue instead of me just sitting up here talking for an hour. So we're going to kind of cover basically the basics of a drive, the benefits and energy savings. We're going to talk a little bit about what you would use in front of a drive and why. Then we're going to talk a little bit about the drive and some basic troubleshooting things with the drive. We're also going to talk about what comes after the drive and why you would need it, depending for different applications. So, going to cover what a VFD is. And it's funny, it's real funny I say this because variable frequency drive, anytime I call anybody anymore, I say variable speed drive. On the phone, nobody can, for some reason, that's hard to say. What's a variable frequency? What? Give me a variable speed drive. We're going to talk about how it kind of controls the speed of a motor, physically how that happens. What are the benefits of using a VFD? Why do we want to use a variable frequency drive? How does it improve process control or, our process control? But the big thing right here is the biggest reason we use it. We're going to talk about how it saves money and energy. So, starting with the basics. With a drive, this is our P1000, which is actually an industrial drive. All drives kind of work the same. And we're going to cover about what we're going to cover a little bit about what comes before the drive. We've got fusing, we've got line reactors, we've got breakers. First, before we get there, we're going to talk about what we're replacing, which is a motor starter. Everybody knows what a motor starter is, right? You got basically a set of contacts that pull in and instantaneously runs from that motor from 0 to 60 hertz within just a split second. Problem with motor starters is 1, you can't control the process. 2, you're using full energy. But 3, every time you start that motor, you'll get 6 to 8 times full load amp inrush current. So if you got a 100 amp motor, that's 600 to 800 amps for a split second. And if you're a building or a company that gets charged for peak energy demands, so like whatever your peak is, that's like your 15 or 30 second interval. That's a big hit. Also, if you're on a fan with belts or a pump with belts, you ever start a motor, you see those belts, they're jumping, they're hopping. A lot of wear and tear on the belts. And that's this cross the line starters, you'll find you'll end up having to replace the belts often. So that's something else that we're going to do with the drive. As we slowly ramp it up, we're going to get rid of that inrush. We'll get rid of that hard hit on the belts and the pulleys and the shivs and everything. And we're going to save energy and we're going to save equipment. What will a VFD do? Protection. We're going to provide some kind of branch circuit protection. We're going to protect that motor. We need circuit breakers, and the circuit breakers will protect the VFD on the input side. We could have fuses and we could have line reactors. And then we got something called harmonic filters, which we'll touch a little bit. That's a whole nother presentation outside of this. Harmonics are created by the way a drive works, which is when we take AC and make DC. And we'll touch on that, but that's a whole nother presentation. Before you have a drive, you got to have some way of getting the electricity to the drive. So on the input side of the drive, And by coding, you've got to have a disconnecting and a short circuit protection feeding that drive. So one of the most common things we have now, it used to always be fuses, but one of the more common things we're seeing now is we're using circuit breakers. Circuit breakers, they serve as the disconnecting means to disconnect power from the drive. They help us for safety for lockout, tagout procedures. There's different types of, if you see you drive in a panel, we can have different types of handles to operate that breaker. They can be through the door, or they can be a flange style, which is a pull down style you've probably seen. They provide instantaneous overcurrent protection. So like if there's a short circuit, it's going to protect the drive from a short circuit, or protect other equipment from the short circuit if the drive short circuits. Nice thing about a circuit breaker is once it's tripped, you can reset it, as we all know. So unlike the fuses back in the day, for electronic equipment, we always used fuses. The problem with fuses, you got to replace them. With a breaker, you can reset it and start over. Connections. Go back to the breaker. We're feeding power in. Power's coming out of the bottom of the breaker. Power's coming into the drive. It's going to connect to the drive through some terminal or something somewhere. The big thing about connections is always, if you go back to any electronic equipment, I don't care if it's a switch gear, electrical, anything that has electricity, you go back to do maintenance or do a checkup a year or two later, retorque your connections. All these connections, one of the leading causes of drive failures and most electronic failures are loose connections. You may have had customers where you have a thermal gun to check for hot spots. Excuse me. That's caused by usually loose connections. If you think about it, especially if you've got a stranded wire even, if you've got a stranded wire, you crimp that down, you start, and every time you start that drive, current's flowing through it, that's heat. That cable is expanding, it's contracting, expanding, contracting as every time you operate it. So what you want to do, and so then that's going to work slowly, it's going to work loose. So one of the ways you can protect your customers and prevent some headaches down the road is every time you go back, if you've installed a piece of electrical equipment, at a minimum, if you're back in there a year or so later, get in the habit of retorquing the main connections at least. It'll save you a lot of headaches down the road. Trip ratings and sizes. Most breakers are sized to 10 times the full load ounce the device is protecting is kind of around where the common is. That'll give you, if you had the starter at 6 to 8, you can handle it. They can be single pole, 2-pole, or 3-pole. Now, for drives, we don't care about single pole, but we do look at sometimes 2-pole, and then we always have 3-pole. And we'll talk about that here in a second. So that's breakers. That's the most common way we're now protecting, we're putting out there for drives. Thing also about breakers though, make sure you have the right style breaker. Some older style breakers don't trip fast enough for sensitive electronic equipment. So you can have a problem if you've got an old style breaker and you get a short circuit. This happened in a school district here down around Akron. You get a call, we go in and look. They had mounted drives in a boiler room. They had mounted what we call type 1 drives, which are just finger safe, so there's no protection from water, on the wall right beside the boiler. Well, what happens occasionally with a boiler? You pop a relief valve. They popped a relief. All that water came down on the drives. It tripped the drives off. It fried the drives. Well, whoever had run the panel had just used regular breakers. Those breakers didn't trip fast enough. They actually tripped the 800 amp main feeding the whole school instead of the 40 or 50 amp breakers on the wall, because that tripped quicker. The surge was so fast, they got the main before those tripped. So the key about breakers, and it's the same thing we're going to talk here in a minute about fuses. Biggest thing, make sure the connections are tight, retorque them if you come back to do maintenance later, and make sure you got one that's designed for the type of electronic equipment you're protecting.
On a breaker, what do you think the failure rate is? How many times can you reset it without it changing its parameters?
On a breaker, that actually I don't know. Anybody else got an idea on that?
I heard of the trips twice, it's suspicious.
Yeah, I haven't even thought about that, a breaker, in a long time. That's a good question. Something we'll have to, maybe we'll follow up on that if somebody write that down.
QOs and the home lines have a very limited shelf life, but the heaters are unlimited. So that's an electrician years ago.
And the interrupt rating on them too. The interrupt rating on them too, I would think would be another key. Yes.
You want to make sure you have them set properly. Like I think NEC coding is talking about for a breaker feeding a drive has got to be like 125 to 150% of the drive rating. If you don't have a breaker, and on larger drives now, they're requiring us to actually, if we have a breaker, we got to put fuses back in them. Make sure the fuses, this is the same thing. This is another topic that could actually be a whole hour discussion, is different types of fuses. When I was a young whippersnapper, like kind of skinny like you, I had a guy tell me, fuse is a fuse. Well, he kept blowing his, he didn't have a slow blow fuses on his cross the line motor, and he kept blowing them. He couldn't understand why. So just like with breakers, biggest thing about fuses, make sure you've got the right ones, because as you see here, there's several different types of fuses. And there's way more than this. This is just some of the examples. Make sure you got the right type fuse for the equipment you're protecting. It's very, very important. You got slow blow, fast blow. And, slow blow obviously would be for like if you had a feeding a motor with a cross the line starter, you got to be able to handle that inrush. And if you had a fast blow fuse on it, as soon as you got 6 to 8 times, it's going to blow. Biggest thing about fuses, and I always get a kick out of this being in here, because you're all technicians, most of you, but it's also just still a good reminder. To check a fuse, what's the number one thing you got to do if you want to check a fuse? Take it out of the circuit.
Yeah. Oh, yeah. Put it on a middle.
We've all done it. So you have I've done it, and I hate to admit it, I've actually checked fuses and like, 6 ohms, it's good. No, I was reading parallel circuit. So just a simple little easy reminder that sometimes you get in a rush, you may forget. If you think you got bad fuses, you got to take them out of the circuit and then check them to see if they're blown. And just like with the breakers, the connections, once again, are so super important. I'm going to beat that horse a lot because that is one of the leading causes that we get with electrical equipment failures. So, breakers and fuses are how we can provide power, provide short circuit protection feeding the drive, and they're also what we provide a disconnecting means. One of the other more common things you'll see is what we call a line reactor. We use line reactors for a couple things. One of the biggest is, I think I briefly mentioned harmonics earlier. Harmonics are, when we're taking AC and we're making DC, and we'll cover this here in a little bit in a minute, we don't use the full sine wave. We're only using the peaks of it. So we're distorting the sine wave that feeds the drive. That distortion of the sine wave is called harmonic distortion. And so one of the things, a drive will distort a sine wave 80%. So if you get enough drives in a building, normally the transformer feeding the drives will just basically absorbs it and kind of says, I got it, and fixes it. Well, but it's additive. Eventually, if you get enough distortion, enough drives, and we're all adding drives to more and more buildings, you get enough drives in the building, what'll happen is the transformer can't handle it anymore. It's getting too much distortion. And it'll start to overheat the transformer. You may have sensitive electronic equipment start to fail. And one of my distributors, he has a real good way to describe this. He says, you ever been at a gas station and you're pumping gas and the guy beside you is topping off his tank? You can feel those pulses in your hose, even though you're just pumping straight. That's distortion. So now if you only got 2 pumps and the guys beside you topping off, you're going to feel it. But now if you're at a Buc-ee's with their 100 pumps and a guy's 100 pumps away topping off his tank, you're not going to feel it. That's a giant transformer. It just smooths out the system. But then you get 10 guys topping off. Maybe 10 pumps away, somebody fills it, but you still don't at the other end. But all of a sudden, you just keep adding drives, more people topping off their tank. So if you got 90 people topping their tank off at the same time, guess what you're going to fill? You're going to fill it. That transformer can no longer absorb it and handle it. That's kind of what harmonics is. I said all that to say why we use line reactors. One of the biggest reasons we use line reactors is the drive distorts the harmonics on the AC sine wave 80%. This will cut it in half. And it has some other things that we'll talk about here in a second, but that's the biggest reason we use is to reduce that harmonic. So like said, now instead of 90 people topping off their tank, we just cut it down to 45. So we're further from having troubles.
Question.
Yes.
So when you're having the harmonics and that, and you said there's, the transformer job's taken care of, the harmonics and for the most part.
It's not its job, but it just does it.
It does.
Yeah.
So at any point in time, with that being said, can that cause that transformer to basically overreact and cause a spike in power?
I don't think I've ever, not that I know of. It'll start to overheat. What it'll cause the transformer to overheat. It'll cause the transformer to fail. But what'll happen is you'll
over voltage.
Not an over voltage, no.
Okay.
No.
That's,
We need a true RMS reading to get harmonics.
Well, we put a scope on it for harmonics. And the spec actually is IEEE 519, which is what we have to adhere to, is 8% or 5% voltage and current distortion at the transformer feeding the building. So once again, the entire system, if you got one drive out there causing it, a 10 horsepower drive on the other end of the building, by the time it gets back to the transformer, it's all been, you're not going to notice it. That's that guy 100 pumps away.
yeah.
But if you get 50 drives, all of a sudden, now you're going to notice that. And that's where you get that distortion. So you put a scope on it, and you can see that distortion.
One time in 16 years I was at Veteran College, I put a clamp-on ammeter around neutral, and it said that was 180 cycles. So that was the
Third harmonic. And that's what.
One time in 16 years I was there.
And the harmonic distortion where we have issues is what we call the third. Oh shoot!
Third harmonic.
Thank you. The third harmonic, and the third and the fifth. It's basically multiples of 60.
Right.
So when you look at the scope at 60 hertz, you won't notice it, but at 180, you see all the distortion, and then at 5 something, you see the distortion. So it's at the third and the fifth harmonic are the worst ones we have to deal with, and that's why we got other equipment. If you start having major issues, there's things we can put filters. There's other things we can put on. But they'll do it more than this. But in general, if you're not having trouble with, just one second, if you're not having trouble with the transformer or any other equipment in the building, you're probably okay. And yes, go ahead.
Okay, office buildings that have cubicles,
Mm-hmm.
they have a wire for 3-phase, the black, the red, the blue, and they also have the neutral. The neutral is double sized because the harmonics stuff, the measured harmonics on the neutrals overheat.
So they oversized the neutrals for
The
that.
neutral is supposed to carry the unbalanced current. So if you have the red, the black, and the blue, the neutral is going to be less. But with harmonics, the neutral is more than the red or the black or the blue.
Interesting. And the thing is, if you're having harmonic issues, you're probably going to be doing more than this. There's other things we can do. There's special drives we can use. And things. So if you've got a customer and they're having major issues with like sensitive labs, or they are having troubles with their transformer, or breakers tripping just unexpectedly, and they've just put some drives in, maybe this is something that can actually solve some issues pretty quickly. Especially if they put a decent sized drive or put 4, 5, 20 horsepower drives in, and all of a sudden they start having issues, and that's something they're probably having some harmonic issues because they've added some more guys topping off their tank.
Now, do they use line reactors on the individual unit or on the transformer?
Yes. No, on the drives. I'm sorry, on the drives, not the transformer.
The inlet or the outlet side of the drive?
Yeah, no, the inlet side. It does a different job on the outlet side. We'll cover that in a little bit, though. So It's on the input side of the drive, and it's mounted by the drive on the input side. And I lost my train of thought now. And on the output side, we do it it's actually to protect the motor for other reasons. It's the same die. Oh, basically, this is a one-to-one transformer. It's a big coil of wire. That's all it is. It's like a one-to-one transformer. So it does, by doing that, as you can see, it uses inductance. It proposes any rapid changes in voltage. That's the other thing you can do. It can protect the drive. Like if somebody hits a forklift and they get a surge through the building, that can help protect the drive from other surges or brownouts and stuff like that. It can help protect the drive from that too.
On that reactor, is it protected in any way to clamp that voltage?
Well, that's what the inductance does. It will clamp that voltage. It naturally it opposes rapid changes because it creates a big magnetic field. That's what that does. That with any quick change, it's going to have a tendency to suppress it. It also prevents, if there's any of this noise coming from other equipment, it'll keep it out of the drive. That's usually not a problem we worry about too much, but it does do that. It prevents drive noise from getting back on the incoming line. That's what we've been sitting here talking about for the last 10 minutes. And it reduces the harmonic distortion that we talked about. It actually cuts it in about half. All right. So really, I mean, feeding a drive, the biggest things we want to make sure is we have a short circuit protection. We have a means of disconnecting and isolating the drive. And then sometimes we may need something for harmonics. That's it. That's pretty much all we think about for feeding the drive for the most part. If you get outside of that, let's talk. We can discuss more. Now, the drive itself. There's three main sections that make up a VFD. There's the input rectifier section, converter section with the pre-charge circuit. That's what causes all our harmonic issues. That's also what we need it. There's a DC bus capacitor bank. And then there's the output section. So on the input side, this is the diode bridge. Has this got a light on it too?
Yes.
Yeah. So this is the diode bridge. This is what's taking AC and making DC. And if you know how a diode works, I know you do. So does anybody else know what a diode does?
The check valve.
It's a check valve. It's an electrical check valve. And it's one of my favorite things to say to people that are being like self-centered. I'll go, you quit being a check valve. And most people don't have a clue what you're talking about. But that's what a diode does. It allows electricity to flow one way and not the other way. So as a sine wave, we have an AC sine wave. And we'll be using this a little bit later, so we'll do it. And we have we usually have three of these, 120 degrees off, but we're just going to leave one. On the top side of the sine wave, on the plus side, one phase is going to go up this way. And then when it gets down to the negative side, it's going to go down this way. And the three phases are going to keep alternating through. And what we're doing with this diode bridge is we're clipping power here. We're only using this parts of it. We're only taking power to take AC and make DC. We're only actually using the peaks of the sine wave. That's why we're distorting it. Across the line starter, a motor is called a linear load if it's across the line starter. A linear load means it uses power across the whole sine wave. We're a nonlinear load. We only take power right here. It's sometimes called the camelback hump. It basically humps the sine wave. That's what's causing the harmonic distortion we're talking about. But this is what's doing it. That's everything that takes AC and makes DC, though. Your chargers for your phone, your laptop chargers. All now we're doing this new green stuff. All the LED lighting and stuff. That all runs off DC. It's all taking AC and using some kind of diode bridge to create a DC bus. So once again, just like I said with the Buckies, it's additive. So the more you got, the more stuff you have. You add the lighting, you add the drives, you add the battery chargers. Eventually, if you get enough, you're going to have issues. You're going to get to that 90 people topping it off. But this is the input side of the drive. First thing we have is the diode bridge. So this creates our DC bus. And then right here we have a pre-charge relay. You ever powered up a drive and like a half a second later you hear this big tonk like a relay kick in? You'll notice they're usually on larger drives. And the reason we have that is we create this DC bus and we use capacitors to hold that DC bus, to develop it and hold it. Well, when you, a capacitor, and it's going to come again, I'm just going to hit it briefly. When you first apply power to a capacitor, it's an instantaneous short until it starts to discharge up. So every time, if we didn't have what we call the pre-charge relay, and this is actually a resistor, a large resistor. If we didn't have that in series with the capacitors, every time we applied power to the drive, we'd blow it up. So what we do is we create the DC bus, we charge up these capacitors. This resistor that's here limits that rush, doesn't let it, slows, limits the inrush. And then once we get the DC bus fully developed and the capacitors fully charged up, we close that relay, because if we left that resistor in there, we'd never have power. We couldn't do anything. We need full power. So then when that's called the pre-charge relay, once those are charged up, the relay closes and we take that resistor out of the circuit. And now we can have power. These are diodes. Now, as always, this is probably everything I just discussed. It's going to be in the next couple of slides. I'm really good at doing it this way. Rectified DC. This is what we're, I hit the wrong button there. This is what we're talking about. See, I said we only take power here and here. So the way we do it is we take, that's the top of the AC, and then we invert the bottom half. And so we, instead of getting a full true DC, we're actually getting like a little humpy AC. To try to, when we want to make that a flat line, we don't want those ripples on that DC bus. Get too many ripples, that's cause a problem. We'll skip that. Pre-charge relay, we already discussed that. So this is what we're talking about. We take power off, we're inverting it, and we do that, and we get a little ripple. Now that ripple, we want that to be a flat line, because that's one of the ways. There's a couple things we know. If you put a scope on it, you can actually see, instead of the DC, which should be a flat line, if you see a ripple on it, if that ripple gets more than 1 volt, you've got a problem. So you've either lost a phase or your capacitors are going bad. It's one of the ways we can troubleshoot a drive. Put a scope on that DC bus, and if we start seeing, if it ain't a flat line, we know we probably are having troubles with our capacitors are getting close to failure. It might be a time to look at replacing that drive or the capacitors at some point.
So basically, that's how a phase monitor is monitoring the phase, just by checking for that 1 volt.
Not on the drive. No, the drive.
But I'm just talking about a phase monitor in general. On
No,
No.
it's a different thing.
It's a different. Yeah.
Altogether.
Yeah.
I just
It's checking actually the phases, not the DC bus. It's actually checking each phase.
The monitors we use are ICM, and they're phase-to-phase protection.
Okay.
How hard is it to change capacitors on a drive like this?
It depends. Okay, smaller drives, most of them, if they're under 20 horsepower, we say it's not even worth it. On larger drives, you start getting above 40, 50 horsepower. It depends on the brand. A lot of drive manufacturers have gone to modular, to modules. So like a 100 horsepower drive, you got to place, it's in a module. And so you're not just replacing capacitors. Now Yaskawa, we actually still can replace just the capacitors. So it depends on the drive you got. I mean, they're easy to replace on either one. It's just the cost effectiveness. If you have to replace a whole module, it might be time to replace the drive. Whereas if you can just replace the capacitors, it might be cost effective. So it really depends on, but it's not hard to do. You just got to know how to, and there's a procedure because of how you got to, what you got to do for the capacitors and stuff. And same thing with the IGBTs, we'll talk about a little bit. So this is the input section, creating the DC bus. Here's the diode bridge. The DC bus, really, we invert it, so we got these humps on it. That's bad. So the capacitors do a couple things for us. Well, actually more than a couple, but one of the things they do is they actually are what hold, you charge a capacitor up, that's what holds your DC bus. Your DC bus should be, this is a good little troubleshooting tool. If you think you got a problem with your DC bus, it should be about 1.44 times your input voltage. So if you got 460 in, multiply that times 1.44, and you'll be in the 675 volt range, somewhere around there. That's what your DC bus should be. If it's not, you probably either got a problem with your incoming power, or you got a problem with your diode bridge. And this is where I like to stop now. Let's talk about the diode bridge. You think you got a problem with your diode bridge. Does anybody know how they can troubleshoot that? And it's a really simple way to do it. It's so simple, even a salesman can do it. So remember the diode, what is it? It's basically a check valve. What do you have on your multimeter? On every multimeter, if it's a diesel one, you have a diode checker. So you put that on a diode. If you put it one way, you'll hear beep. Hear it the other way, it's an open, right? That's what you need to check a drive. To check the entire input, this diode bridge, you take your line leads off, make sure the drive discharges, make sure that capacitor discharges, give it a few minutes, measure the DC bus. Don't trust that little red LED that we probably paid less than a penny a piece for. Don't trust that didn't just fell on you. Measure the DC bus, and every drive will have a plus and a minus somewhere in the drive. That's your DC bus. Make sure your DC bus is de-energized. Then you take your multimeter, put it on diode. You put one lead on minus, and you put one lead on L1. Check it. One way it should show open. The other way you should get your beep. You do it for L1, L2, L3 to minus. You do it and you check it both ways. One way should be an open, the other way should be a beep. And if you get them all three, then you know the negative side is good. Take that, go to the plus, do the exact same thing. One way's open, the other, and if that's how you can check the entire input section of the drive, just by checking it with a diode checker. Pretty simple, pretty easy. Charging capacitors, this is where we talked about what, see, this shows the y-axis and the x-axis is time, and the other is the voltage, or the current. The red is the current, excuse me. So when you first apply power and the capacitor starts charging, current's through the roof. As the capacitor charges up, then the current drops down.
It's only for a brief period.
Oh, very, very brief. Yeah, not even a brief what?
I before E except after C. Except for weird, that's an exception.
Oh, dang it. I see now, brief period. Hey, I'm from the, did I not tell you in the beginning I'm from the South? But this is why we talked about that pre-charge relay and have that resistor in there. This is just showing it. Capacitors are made up of a semiconductor or a dielectric conductor sandwich. When voltage is applied to conductors, I'm reading this because it's kind of, we've covered it. When voltage is applied to the conductors, the charge becomes present in the core of the capacitor. The dielectric material is simply a non-conductive material. Basically, the capacitor charges up. And it holds a charge 650 to 700, and that's how much times your input voltage? 1.44. So it should be about that. So if it's a 230, it's going to be obviously a lot less than that, but this is for a 460. It regulates the DC bus voltage to eliminate ripple. Remember we talked about these little humps? It's going to fix that, and you'll see that here in a second. Because if that ripple is more than 1 volt on the bus, there's probably a chance that your capacitors are on the way out. And then that's time, if the drive's still working, it's time to, hey, next shutdown, next something, let's talk about it. We need to look at this. And this is what it does. So that capacitor, this is what it would look like if we didn't have capacitors. We have this little rippled DC bus. Capacitor start charges and discharges continually to fill that little gap in and creates a nice flat DC. So they create the DC bus, and they also they hold the charge for the DC bus, and they also make it a pure DC. So they're continually sitting there discharging and discharging to fill in that little gap. So we've talked about the input side, the diode bridge, how we make it, the problems with that. We've talked about the pre-charge relay. We've talked about the capacitors. And for those of you that got a few years on us like me, I see a couple of them sitting here. When I remember being a young guy out in the field and we'd get a little capacitor, charge it up and toss it to somebody. You'd probably get fired nowadays for that. But back in the day, we just laughed and said, ha ha. And ran because they were coming after you.
What is that box underneath the word bridge signifying?
That one, I don't know on this one. I forget what, I'm not sure on this one.
They had some huge capacitors for ships
Mm-hmm.
thing this high, this wide.
You don't throw those at anybody.
Somebody, they charged one of those up for a joke. 2 weeks later, when they took it off, a guy got electrocuted.
Oh, yeah, they don't
Hard
just-
to charge for that long.
Oh, yeah,
And now you have to have a bar across it.
yeah, they discharge very, very slowly unless they have something to take that
You
energy.
have to put a bar across it. for
Yeah.
safety.
14,000 ohm screwdriver.
Yeah.
14,000 ohm screwdriver. I like it. So that's the input of the bridge. This is the DC bus. And then now we got the IGBT transistor stage. This is what now the drive's going to start doing the work to turn the motor. The IGBT is insulated gate bipolar transistor or isolated gate bipolar transistor. It's the exact same thing, just different companies call it different things. The inverter section in most 6-pole drives, this is every drive out there, we have six IGBTs that are going to fire at different times to create what we call a pulse width modulation. Everybody's heard of a PWM drive? That's every drive that's out there for the most part. The transition, they use insulated gate bipolar to switch on and off, and they create the PWM. So an IGBT is basically a fancy diode that instead of it just controlling flow one way or the other, it still controls flow one way or the other, but we can turn it on and off at will as we want to allow that flow. So since it's a fancy diode, guess how you check the output section of a drive if you think you got a problem in your IGBT section?
We did the input side.
You take the diode checker. This time you take the motor leads off. You also de-energize the drive, by the way. You take the motor leads off, and you do the same thing, except now instead of doing L1, L2, L3, you're going for the plus to minus to T1, T2, T3. And you're checking it both ways on all three phases, plus and minus. And that's how you can check the output section of a drive to see if you got a problem with your IGBTs. It's really, I mean, you think about this fancy drive, to truly check the input and the output, all you need is a diode checker. This is a terrible picture. I don't know why it got in here. I'll have to fix it for the next one, but I apologize. So this PWM, pulse width modulation. What we're doing is we're controlling these diodes to create and turn them off. And turn the first one for a little bit, then the next one will hold on just a little bit longer, the next one a little bit longer. And that's why it's called pulse width modulation. And these are the pulse widths. I apologize, once again, you can't see this. So what'll happen is we turn on the first diode, power starts to build up. If you notice, this whole line here is all the same height. So keep it on just a little bit, and this is a power curve, basically, the motor's going to see. Turn the first on for a little bit, shut it off. Turn the next on just a little bit longer, and then power builds up. Shut it off. To the next one a little bit longer, power builds up. And we keep holding that one on just a little bit longer, a little bit longer, a little bit longer, and then create the sign. We start going the other way, shortening it. And then we do it on the negative side, on the negative side here. So for the plus side, we're firing these, and the negative side, we're firing these. Now, this is why it's so important. Hopefully, here we go. This is a little prettier. This is why it's so important, though, to make sure you've got the right motor for a drive. You know, we always say you want to make sure you have an inverter-rated motor. The reason is we're not putting AC out to that motor. We're putting a pulse DC that simulates AC to the motor. And the thing about, I'm going to do it here. The thing about these pulses, you see how high they are? The way DC works, that ain't what really happens. We turn that on, it spikes up, then drops down and then holds open. Spikes up, kind of like that inrush current on the AC, remember? Spikes up, comes down, then holds, spikes up. So actually, the peak spikes are here and down here. They're hot, they're more. So if you're running a motor on a cross-the-line starter, your peak-to-peak voltage, if it's 460, is 460 to minus 460, that's 920. On a drive, because we're pulsing that DC out to it, and it's spiking up and then holding, those spikes, that pulse will be, could be 1200 volts right by the drive. And the way DC works, the further that motor is from the drive, the more those pulses grow. So those spikes will get worse. So if you're 100 foot from the motor drive, it may be 1200 volts. If you're 10 foot, it may be 11. You're at 500 foot, you may be 1500 volts peak to peak. That peak to peak, that's extra heat. That's why you've got to make sure you have the right equipment or the right motors to handle this extra heat that we create because we're pulsing DC to the motor. We're not just sending a pure AC to it. And you can see here what a drive does, obviously, and I guess should have mentioned this in the beginning. Obviously, the way a drive works is we change the frequency, right? So if we've got a motor running in the Americas at 60 hertz, we can slow it down to 30 hertz, saves energy. We'll talk about that here in a little bit. We also lower the voltage down. We control voltage and frequency at the same time. So if you're checking a drive, and this happens, and we still get the calls all the time. Somebody walk up to a drive and they go, hey, drive's running 30 hertz, and I checked the output voltage, it's only 230. That's right. We actually, volts per hertz, our volts per hertz curve, as we're changing frequency, we're changing voltage at an equal proportion. And so if you're a 460 drive and you run 30, your output voltage is going to be around 230. So this is what you'll see. We keep hitting these pulses. If this would be like a 10 hertz pattern, so we're running the motor at 10 hertz, which y'all probably never ever see in the HVAC world. We fire that even quicker. Now we're doing 20, and we just keep doing. So this is how we create the AC, by controlling how fast we're firing these IGBTs. These things are getting fired at thousands of times a second. It's called the carrier frequency. You've probably had to adjust that on the drive maybe at some point or another, because we're sending those pulses out to that motor. Sometimes, the motor on the drive has a whole different sound, and it kind of gets a weird sound to it because we're pulsing a DC. Well, sometimes that sound can be really annoying if it's near an office. So one of the ways you can kind of control that, if somebody's saying, hey, this motor is really high pitched, it's driving me crazy, you can adjust how fast we're firing these IGBTs. It's called the carrier frequency. Usually it's going to be around 4,000 or 5,000 times a second we're firing these. So maybe you can raise it up to 6 or 7, or drop it down to 2. The lower the carrier frequency number, the higher pitch that sound's going to be, but you also have more torque. The more often we fire those, it'll lower the sound, but we won't have as much torque. So there's a nice fine line you got to make sure you're looking at. But you can actually change the sound of the motor by changing how often we're firing these to create those sine waves. Pulse width modulation, we kind of just discussed that. They're either fully on or off. Once again, they're just fancy switches. I call it like a light switch, on, off. Check valve's another way to put it. I like to call these light switches because we control them when we're turning them off and on. Not just by the sine wave coming in. So that's the drive. Let's go back real quick. Really, that's all there is to a drive. Got the diode bridge, the DC bus, and a bunch of IGBTs we fire out to create that pulse width modulation to change the speed and voltage on the motor, control the motor. So that's all there is to it. Now, obviously, there's some controls in there that we can do and do different things, which is beyond what we're doing here, but this is basically how every drive out there works. Any questions on the drive? So we talked about what feeds a drive. We talked about the drive. Now let's cover what we may need after the drive, besides the motor, obviously. Yeah, between the drive and the motor. Most common things we would have is an output line reactor. Normally we call it output load reactor. This has been a misprint that I haven't fixed, and I like it. There's a reason I haven't, because it's the same exact thing we put on the end. It's the same part. Remember, you take a line reactor, you stick it on the other side, the exact same thing. It's just doing a different job. We have DVDT filters. These DVDT filters, remember I said those spikes of the DC bus can be 1,500 volts peak to peak? Well, we use a line reactor, that'll hold them, that'll squelch them down a little bit. But if we still having trouble, or we're going like 700-800 foot, we'll put what's called a DVDT filter, and that actually clips them and keeps it from growing. So it protects the motor. So the further, if you get a certain distance, we may have to add what's called a DVD. That's differential voltage over time. And that's based off distance from the drive. So if the line reactor, it will protect the motor from those high spikes. So if you get out there a couple 100 foot, we'll throw a line reactor. You get out there 400 or 500 foot, we may need to do a DVD-T filter. We're going to talk about motors and multiple motors, because a lot of people don't realize you can actually run several motors off one drive. Drive doesn't care. We'll talk about that here. Output line reactor, same as, it's not only uses the same principle, it's the exact same device. It's the same part, just where we use it. And it's basically a one-to-one transformer. We're using induction. This says 250. Some manufacturers say 150. Some say 200. This is really motor dependent. We get the calls all the time. Hey, I got this motor. Can I run a drive on it? Or I'm at 200 foot. Do I need to put a load reactor on it? It really depends on the motor. Depends on the insulation in the motor. There's a motor manufacturer out there off the record. They say, you don't need anything. Our motor's up to about 500-600 foot. That's how good their insulation is. But I look at this like, everybody remember the Yugo? It was a car, right? It met the spec of a car, didn't it? But what'd you do when you ran out of gas? What was the old joke? You ran out of gas, you threw it away. But it met the spec, didn't it? But it wasn't a Mercedes. They were both cars, but man, they had different materials in them, and they worked different, didn't they? It's the same thing with motors. There's some cheap motors out there that you can get. They meet the spec of a motor, but you start getting more than about 100 foot, 150, 200 foot, you're going to have troubles with that motor. You may burn the motor up. So it's really motor dependent. You really need to know and talk to the motor manufacturer about what they need at what distance from their drive. We use a line reactor if we run more than one motor off a drive. Let me see something real quick. Okay. So we can actually run and y'all see this on fan arrays. Y'all do a lot with fan arrays here at all? We're starting to see this more and more on fan arrays. And you can actually take one drive and run like as many motors as you want, as long as you size the drive properly. Because to the drive, if you got 4 10-amp motors, we just see it as one big 40-amp motor. We don't care. We put a 40-something amp drive on it, and we're good to go. But if you are doing that, there's still slight differences. Even though the motors are all running the same speed, they're all running together, they're all the same motor. If you're doing this, we recommend you put a load reactor on there just to eliminate any issues for multiple motors. Like I said, you'll see this on fan arrays. You'll see like 4 motors on one drive, and they'll have like modular fan arrays now. So that way, and they got redundancy. If one drive fails, they only lose a quarter of the fan array, or whatever, or depending on how they got it set up. The big thing about this, if you do run multiple motors off one drive, got to think about a load reactor. But the other thing you got to remember is the drive is just one big 40-amp motor. So if you did lose one motor, and the other 3 motors are picking up the load, and now they're running 12, 13 amps. If we got 3 motors running 12 amps, that's 36 amps to the drive. We don't care. Hey, we're good. You're over amping those motors, and you'll burn those up too. So if you do that, you've got to make sure you have individual overload protection for each motor. One last thing. And you want to upsize the drive by about 10%. So you add all the full load amps together. And then, so if it's 40 amps, you want to make sure you have a 44 amp drive.
Yeah, so if I have no idea, what is a line reactor? It's basically just a coil of wire?
Mm-hmm. It's like a one-to-one transformer.
Just a coil of wire.
Just a coil of wire. All right. Now, also, if the motor gets too far away sometimes, you maybe start getting nuisance trips on the drive. You get what we call voltage feedback. You can get all kinds of stuff happening. Now, if you have multiple motors and your drive just starts tripping occasionally for no weird reason, you can't figure it out, you may be having trouble. A load reactor may just clear that up, especially if the motor is any distance away. Long motor leads, 250 foot. And the thing is, it kind of carries the same thing as a capacitor. That's what it can cause troubles, and that's when you would have it. And, it prevents this. It prevents the use of what we call voltage doubling, and that's just based off of how the drive works. I'm not really getting into that. So that's when you would use a load reactor. Long distances, multiple motors. weird trips that you can't figure out why they're happening when the motor's a good bit away usually. Load reactors sometimes will clear all that up or prevent issues. Output disconnect, commonly called a line of sight disconnect. So if your drive's in a control room or in a room and the motor's out on the floor somewhere or up on the rooftop, you've got to have what's called a line of sight disconnect, right? You got to have a means to disconnect that motor if you got to work on it. And there's nothing wrong with that. One thing we wish you would do always, at a minimum, make sure your lockout tagout procedure tags out the drive as well. Because you can go out there and trip that drive off, or open that disconnect and take that motor off the line. The drive's just sitting there going, hey, boy, I got really light loaded all of a sudden, unless you've set it up to sense that, which in most cases we don't. It's like, hey, my load's low. And all of a sudden you do your work, you close that drive, and now the drive's been sitting out there putting out 45 hertz the whole time, just not going anywhere. And now you go to close that disconnect because you finished your work on that motor. You're trying to take that motor, instead of ramping it up slowly like we do with a drive, you're trying to go from 0 to 45 hertz instantaneously. Drives don't like that. You're probably going to let the smoke out of the drive and get a new drive. So at a minimum, make sure your lockout tagout says tag out the drive if you're working on that motor and opening that line of sight disconnect. What we really would like to have is some auxiliary contacts that if somebody opens that disconnect without tagging out that while the drive's still running, it'll trip the drive off. From the VFD load, I mean, that's disconnect. We just kind of discovered that. You know, it's going to be to isolate the motor from the drive, but once again, you don't want to close it back if the drive's running. So really on the output side, that's the most common things we might use. There's some other things that could come up in different scenarios. If they're that, you're talking to some engineers. So we've got load reactors and we got output disconnects. That's pretty much all we're ever going to see between the drive and the motor in most applications. Boom, motors and loads. Loads can be, we're going to talk a little bit about loads, and we're not going to do a lot of time on constant torque because that's more industrial, and variable torque. But this is why we're here, and this is why the biggest reason drives exist is for variable torque loads. A constant torque load, this is more of an industrial we see. You're in the centrifugal pumps and fans, they're called variable torque loads. But a constant torque load is something like a conveyor. A conveyor, the torque required to move that load doesn't matter how fast it's going. It's based off the weight of the load on it. So whether we're running, this is the speed on the bottom line here. So whether we're running a real low speed or we're running full speed, the torque is pretty constant across that, no matter how fast we're spinning that motor. That's called a constant torque load. It actually takes a little bit heavier duty drive than we use in the HVAC world normally. What you have almost always are variable torque, centrifugal pumps and fans. In Liberty tunnels in Pittsburgh, my drives are on those tunnels, on the fans in those tunnels. Those fans are about 10-foot diameter. After they put the new fans in, before they got everything, the covers and all, you could literally walk up with your hand and turn those 10-foot diameter fans like it was nothing. Because all you were doing was, once they had them balanced, all you would do was overcome the friction of the bearings. Doing no work. That's why variable torque loads down here, they take almost no torque to get a fan going because it's not moving any air. Same thing with a pump. We're not moving anything. So to get it going, doesn't take much. To get this going, we need a little extra oomph at the bottom. So these drives are rated for 150% overload. Your HVAC drives are rated only for 110 because we should never exceed that 110% at all because it takes nothing to get going. But the faster we go, we get out here to 100% speed, 60 hertz. This is almost a straight line up and down. This is where we can save a lot of energy because variable torque loads, the faster it goes, the more power, torque, and power it takes to run that fan. The rule of thumb, if you can slow that fan or that pump down 20%, it saves 50% of the energy to run that motor. It's due to infinity laws, which we'll discuss here in a second. But, so this is where we save all the money, and this is why we have drives on everything out there. So you think about that. If you've got a system, an air system, and you can slow it down to 48 hertz from 60, you cut the energy required to run that motor in half. And a 10 horse motor, if it's running 24/7, which most of them aren't, but costs around $10,000 to $15,000 a year to run it 24/7. So you run it 8 hours a day, it's still going to be several $1,000s a year for a 10 horse drive that costs, a couple $3,000. Doesn't take long to pay for that drive if you can slow it down. So this is
If you can slow it down.
if you can slow, which in most applications.
Out there with ductwork and stuff not being sized right, trying to carry static pressure, and they got problems with pumps or piping's not right. We can't maintain a differential. I mean, I know guys that are amping out their motors and running their VFDs 80% instead of 60. I mean, it's 80 hertz. Yeah, 80 hertz. Yeah, I mean.
And the thing you got to watch with that, you can run it, because our drives you can run up to over 400 hertz. I mean, over 500 hertz.
Sure.
But you got to there's a certain point you got to be careful with that, because just like this little bit changes here, as soon as you get above 60, that's almost a straight line up.
Right.
So as you start going 70 hertz, the power just is going through the roof. And you got to watch the torque curves. Like a lot of motors and even the fans, they have torque curves. They have curves. And somewhere above 60 hertz, at some point, you just lose it. So you might get to 80, and then 82, you have no flow. It just drops off. So you got to be very careful when you're going above 60. People do it all the time for balancing reasons, for different things. Like what you're saying, people are trying to get more flow. Engineers slightly under-designed it and say, hey, can you give me 10% more? There's a lot of reasons we do it, but you've got to be careful with it, because at some point you will, one, this drive's got to be sized big enough to take that extra current. And two, at some point you can't go too high.
Because the fan law is the cube of the speed.
Same thing.
If you want to run double the speed, it's 2 times 2 times 2. 8 times the force.
That's the same rule we use in the 2050. That's the infinity laws. And the infinity laws are what we use, flow. Flow is proportional to change in speed. So if you've got airflow or water flow, whatever it is at 100, it's 60 hertz. If you slow down to 30, that flow cuts in half. But power is the cube of it. So if you drop it 20%, that's 0.2 times 0.2 times 0.2. That's why 20% gets us 50. Yeah. At 30 hertz, you're like 20%. I mean, it's
28 times 28 times
yeah. So that works the other way too, as he was saying that the infinity laws goes the other way. If you go above, every hertz you go up is cube of that in power and torque required.
I think you call some HVAC. These buildings are 2 years old.
It's design issues.
Nightmare. Yeah. Oh, it's terrible. Well, and then not to go off subject, but I had like 80 CFM on this one air handler, right? And the thing, VFD is running 60 hertz. This thing's wide open. So I shut it down, climb in there, and all the duct insulation inside, just peeled, laying in all the vanes and the ductwork. Oh yeah, sent Matt in there. He was climbing through the duct. That was terrible.
So we kind of go through this. We've already kind of covered this. Variable torque applications, linear curve. That's that curve we talked about here. Pump or fan can be considered a variable torque load. In the VFD, we only set it for 110% overload. So that drive is the size because we don't expect to have any torque at the bottom of it running at slow speeds. And in most of your applications, I doubt you ever go below 20 or 25 hertz. Because below that, you're not doing any work anyway. You might as well just shut off. All right. So that's how we save energy. Let me see, go right here. That's how we save energy, because this right here, a little change in speed, big change in power. Now, to size the drive. What do you need to size a drive? Anybody know? If somebody calls you up and says, hey, I need to put a motor on this fan. I put a drive on this motor on this fan. What do you need to know?
How much flow?
Voltage, full load amps.
Application.
I could kiss you, because you didn't say horsepower. You said full load amps. That is the biggest thing, is we need to know the voltage, because all motors, or most motors out there, have a 234, they are dual rated. Drives are not. What we put in is what we get out. And you'll be surprised how often that still happens. Somebody calls and says, hey, I let the smoke out of this drive. I put a 230 drive on a 460 load and it blew up because they didn't realize they're not dual rated. Oh, actually, this actually says it right here, but I forget. This says it behind me. All you had to do was read the screen. I was all happy. I was all proud of you. No, but the voltage is the in the industrial world, we got to worry about constant torque or variable torque loads. You guys are all dealing 99.9% of the time variable torque loads. Full load amps is more important than horsepower, and the reason that is every drive manufacturer out there, we size our drives based off of NEMA B 1800 RPM, the most common motor out there. So 4-pole 1800 NEMA B motor. We all size our motors drives based off that. What if you have a 8-pole motor, high torque motor? So a 20 horsepower 8-pole high torque motor is going to draw more amps than an 1800 RPM motor. A 900 RPM motor has more torque and it's going to draw more current. You can get yourself in a situation where if you got certain motors, you may need to oversize the drive by at least one size or sometimes. So that's why the full load amps are the most important things. So really the biggest thing I need to know, the number one things I need to know the voltage, so I don't, because drives aren't dual rated, it still happens all the time. And I need to know the full load amps. Occasionally you may have a positive displacement pump or something like that. Those are constant torque loads. You got to make sure it's a centrifugal pump. So in those cases, then you're good. Fans are centrifugal pumps, which is 99.9% of what y'all do. But voltage and the full load amps, and I can comfortably size it to know what I'm doing. But then you got to start asking things like how far the motor is away and stuff like that. But that's the minimum we need to know from voltage and the full load amps, the size of the motor. And all that's going to be on the motor nameplate. Got a customer calls you, say, I'm going to say, send me a picture of the motor nameplate if they got the existing motor out there. Because it also gives us the installation class. And as long as we see a type F, we're usually okay. Not always, but usually as long as we see at least a type F installation, we're okay. But we really want to see the motor nameplate. If they can get a picture of it, send it to us. That makes life so much easier. We can size it. So that's output, variable torque, motor nameplate. Real quick, we'll go through a few of the benefits of why we have VFDs. We use them for process, level control, pressure, flow, some of the things we've just been talking about. We can lower maintenance costs, as we talked about earlier, because you're not hitting those loads with, from 0 to 60 hertz right away. It's better for belt life, bearings, motors. We don't need a cross-line starter, so you don't have to worry about peak loading. Can limit the torque. You can actually set drives up to limit the torque. So like if you've got a condition where you're worried about over-torquing something, you can actually set a torque limit on the drives. We can run multiple motors from a drive. So there's a lot of different things we can do. We can run high-speed applications. Sometimes your guys want to overspeed them, go faster than 60 hertz. But the number one reason we see it in a lot of applications is right here. We can save a lot of money. The payback time on most drives, if you can slow it down to 40, 50, 60, or 40, 50 hertz, somewhere in that ballpark, is usually less than a year. And now they're putting that money in their pockets. And there's software out there that can show that payback analysis, and it's really good software. We've already discussed about energy savings, and we've talked about the infinity laws, which is what we're talking about. That's the cube of the speed. And that is it, except for unless you got some questions.
No.
Or some answers, Phil. I'll take answers too.
You want to get up there and teach?
Bannerot College had a $3,000 variable speed drive, and they replaced it with one of the variable frequency guys sent us 3 gifts, the little tiny ones. So we hooked those up for 480 because Bannerot had 12208 and 277 480. So his great big job
Glad you said that. Keep going.
was 30 years old. That was a monster.
I'm glad you said that because you brought up single phase earlier.
Yeah.
So one last little topic we really cover. Remember I said how drives work? We take AC and we make DC. We don't care if we got 3 legs or 2 legs to do it. We're still going to create that DC bus. So you can run drives off single phase. You'll bring power, you bring your 2 legs into L1 or and L2 usually is the most common. The thing you got to remember though is now you've got all that current coming in 2 legs instead of 3. We have to oversize the drive. So if you got an application, so then we're going to, because whether you got 3 legs or 2 legs of power doing it, we're still going to create that DC bus. These are still going to fire and create the 3-phase output. This is really nice because if you got, I mean, you get up to 5 or 10 horsepower single phase motors, they're expensive and you can't control them. You can run a 5 or 10 horsepower, 20 horsepower motor, 3-phase motor using single phase in the drive as long as we size the drive properly. The old rule of thumb that we used to use back in the day when drives were big and they had extra capacitance was 2-to-1. That is no longer the case. Some people out there still will try to do that. You literally do not size your drives if you got a single phase input at 2-to-1 because you may run out of power when you get up around 60 hertz. Because the drives, we're making the drives smaller. Everybody wants, less space. We don't have extra capacitance. So we don't have that extra. Now it's usually 2.5 to 3 times we have to upsize that drive, but we can do it. I just want to make you aware of that because you brought that up earlier. We can take single phase in and create 3-phase and run a 3-phase motor. We just got to size the drive properly.
Well, one question I always ask electricians or HVAC people, what 2 things determine the speed of an alternating current motor? 2 things.
Number of poles
Number of poles
and the frequency.
and frequency. They always say number of poles and voltage. So if you have a 120 volt motor and you hook it up mistakenly to 230, you think it's going to run twice as fast. No, it's not. It's 60 hertz.
60 hertz.
It's going to have twice as much current because you have 240 pushing the stuff through it instead of 120, but it's not going to go twice as
No.
fast.
No, it's frequency
It's
and
going to burn it up.
the number of poles on the motor
Twice as much smoke.
for half the time.
There you go.
And the definition, I have like over and over and over again, what is the definition of single phase less than 3 hots? 1 hot, single phase. 2 hots, single phase. 3 phase, 3 hots.
Yes.
3 phase, 3 hots. 3 phase, 3 hots.
Yep.
If it ain't, it's single phase. If this building, and I know it does have 3 phase, and I call the electric company, I say the building is single phasing, they know that less
You've lost 1 leg.
than 3 hots are working.
You've lost 1 leg.
You lost a leg.
Yeah, you've lost a leg. And you know what that does in a drive? You lose that leg. That's when we get that ripple, and we got a problem. That's the other. If the capacitors are your single phase of drive, you get that DC ripple. So that's why we also got to oversize the drive because to minimize that DC ripple.
Do these tell you if you lose a phase?
What's that?
Will these lock out?
Some can, some can't. It depends on the drive and if they've got what they've got on the input side.
I have some trained VFDs and they go into a phase lockout.
Yeah.
Go into a line.
What's the general discharge time after you shut a drive down?
3
Cigarettes.
cigarettes.
Yeah.
And it depends on the size of the drive and everything. But
Size capacity.
when that voltmeter on DC bus says 0,
Or when your assistant says it's a 0.
and the guy went like, "We're good."
On a ship, 2 weeks, was charged up just for a joke and went across the sea for 2 weeks, and a guy went across it and it killed him. So it held the charge for 2 great big capacitors.
Oh yeah, they won't. I mean, they just sit there and hold the charge. I don't know what the time. It's a long time.
If there's no using it, it's going to sit.
It's just going to sit there and charge.
It's a battery.
It's basically a battery, waiting to get rid of its voltage. It's
Quickly
quickly.
as it can.
So All right. Well, thanks for your time, guys. Appreciate
Thanks,
it.
Tony.
Thanks for having me.
Appreciate it, sir.
Hopefully you learned something. Now, if Phil learned